Johannes Kepler was a German astronomer who lived from the late 16th century to the early 17th century. Regarded highly in the scientific community, he accurately described the process of vision, explained the behavior of light in telescopes, and most famously, formulated his 3 laws of planetary motion. Here, we will be going over the derivation of his second law, the law stating that the areal velocity of a planet's orbit is constant. To start the derivation of Kepler's second law, we have to understand the idea of areal velocity. Essentially, areal velocity is the speed at which area is swept as a particle moves along a curve. Getting the areal velocity formula requires us to go over the formula for the area of the sector of a circle. We start with the formula for circular area, which is A equals pi r squared. To find the area of a sector, we need to account for the fraction of the circle that the sector encompasses, and we do that by multiplying the formula for circular area by theta over 2 pi, theta being the central angle for the sector, and 2 pi being the radians in a full circle. That leaves us with the formula A equals theta over 2 pi times pi r squared, and this can be simplified to A equals 1/2 r squared times theta. Going from this formula to the areal velocity formula is actually fairly simple. The rate of change for area is dependent on the rate of change for the central angle, so with that in mind, we get dA dt equals 1/2 r squared d theta dt. Here, we can replace d theta dt with omega, since angular change over time is angular velocity. Now, using circular motion, we know that omega is equivalent to tangential velocity over radius, which allows us to further alter the areal velocity formula to dA dt equals 1/2 r squared times v over r, which then can be simplified to dA dt equals 1/2 r times v. Now, it's time for vectors. The variables of r and v are represented by vectors, which will help us figure out why the areal velocity is constant. Now, because these variables are vectors, that means that the product between them is the product between 2 vectors. The question then arises, is this a dot product or a cross product? That question can be answered by looking at the formulas for each, and with that considered, we see that this must be a cross product because the angle between the 2 vectors is 90 degrees. We're now left with the formula dA dt equals 1/2 r cross v. From here, we need to prove that dA dt is constant. If it is constant, that means that the derivative of r cross v is 0, because the derivative of any constant is 0. Following the formula for the derivative of a cross product, we get the derivative of r cross v equals r cross dv dt plus dr dt cross v. We can replace dv dt with a because acceleration is change in velocity over time, and we can also replace dr dt with v because velocity is change in position over time. Finally, this gives us the derivative of r cross v equals r cross a plus v cross v, and this equals 0 because r is parallel to a and v is parallel to v, which means that by the definition of cross product, both of these cross products equal 0. As stated before, this means that r cross v is constant, and by extension, so is the areal velocity. With this, we have proven Kepler's second law.